How do we know what the universe looks like? How can we measure the distribution of matter and energy across billions of light years? How can we test our theories of gravity and cosmology using the cosmic microwave background radiation, the oldest light in the universe? These are some of the questions that scientists are trying to answer by creating maps of the universe. Hello and welcome to Curiosity, where we explore fascinating and interesting topics about everything. Today's topic is, can we make a perfect map of the universe? But what does it mean to map the universe? Unlike mapping the Earth or the solar system, we cannot send probes or satellites to distant galaxies or clusters. We have to rely on the light that reaches us from these objects, and how it is affected by the intervening space and time. And we have to deal with the fact that the universe is not static, but expanding and evolving over time. One of the main challenges of mapping the universe is the presence of dark matter, a mysterious substance that makes up about 85% of the matter in the universe, but does not interact with light or other forms of electromagnetic radiation. Dark matter influences the formation and evolution of galaxies and clusters, and also bends the light that passes near it, creating a gravitational lensing effect. By observing how the light from distant sources is distorted by dark matter, we can infer its distribution and properties. One of the most powerful sources of light that we can use to map the universe is the cosmic microwave background radiation, or CMB for short. This is the remnant of the primordial fireball that filled the universe when it was only 380,000 years old, about 14 billion years ago. The CMB is a snapshot of the early universe, and it contains information about its age, geometry, and composition. But the CMB also carries the imprint of the matter and energy that it encountered on its way to us, such as the dark matter and the dark energy that drive the accelerated expansion of the universe. Recently, a team of researchers from the Atacama Cosmology Telescope Collaboration, or ACT for short, have created a groundbreaking new map of dark matter distributed across a quarter of the sky, extending deep into the cosmos, using the CMB as a backlight. The map reveals the most detailed features of the invisible cosmic web of dark matter that surrounds and connects galaxies, and it confirms Einstein's theory of how massive structures grow and bend light over the 14 billion-year lifespan of the universe. The ACT is a 6-meter telescope located in the high Chilean Andes, and it has been observing the CMB since 2007. The ACT team used a technique called gravitational lensing to measure how the CMB light is warped by the intervening matter. By comparing the observed CMB with the predicted CMB based on the standard model of cosmology, they were able to reconstruct the mass distribution along the line of sight and create a map of the dark matter. The map covers about 17,000 square degrees of the sky, which is equivalent to about 40% of the area of the Earth. It spans a range of distances from about 6 billion light-years to about 11 billion light-years, corresponding to a range of cosmic epochs from about 5 billion years ago to about 9 billion years ago. The map shows the large-scale structure of the universe, such as the filaments and clusters of dark matter, as well as the voids where there is less matter. The map also shows the effects of dark energy, which causes the structures to grow more slowly over time. The map is consistent with the predictions of Einstein's theory of general relativity, which has been the foundation of the standard model of cosmology for more than a century. The map also agrees with other independent measurements of the cosmic expansion rate, the Hubble constant, which has been a source of tension among different methods. The map provides further evidence that the standard model of cosmology, which includes dark matter and dark energy, is a good description of the universe. However, the map is not perfect, and it has some limitations and uncertainties. For example, the map is based on a statistical analysis of the CMB fluctuations, and it does not resolve individual galaxies or clusters. The map also depends on the assumptions and parameters of the standard model of cosmology, which may not capture all the complexities and variations of the real universe. The map also has some noise and errors, which may affect the accuracy and precision of the results. The ACT team is not the only one working on mapping the universe using the CMB. Another team of researchers from the Dark Energy Survey Collaboration, or DES for short, have also released a new map of the dark matter using the same technique, but with a different telescope and a different region of the sky. The DES is a 5-year survey that uses a 4-meter telescope in Chile to observe hundreds of millions of galaxies and supernovae. The DES team used the CMB data from the South Pole Telescope, or SPT for short, which is a 10-meter telescope located at the Amundsen Scott South Pole Station. The DS map covers about 5,000 square degrees of the sky, which is equivalent to about 12% of the area of the Earth. It spans a range of distances from about 6 billion light-years to about 10 billion light-years, corresponding to a range of cosmic epochs from about 5 billion years ago to about 8 billion years ago. The DS map is similar to the ACT map in many aspects, such as the large-scale structure and the agreement with Einstein's theory. However, the DES map has some advantages and disadvantages compared to the ACT map. For example, the DES map has a higher resolution and a lower noise level, which allows it to detect smaller and fainter structures. However, the DES map has a smaller sky coverage and a shorter depth, which limits its ability to probe the largest and most distant structures. The DES map also has some systematic errors, which may affect the reliability and consistency of the results. The two maps are complementary, and they can be combined to create a complete and accurate map of the universe. The two teams are collaborating to cross-correlate their data and to compare their results. By doing so, they hope to improve their measurements and to reduce their uncertainties. They also hope to test their assumptions and to look for any deviations or anomalies that may indicate new physics beyond the standard model of cosmology. Mapping the universe is an ongoing and challenging endeavor, and it requires the collaboration and coordination of many scientists and instruments. The ACT and DS maps are not the final word, but rather the latest milestone in a long and fruitful journey. There are many more maps to be made, and many more questions to be answered. By mapping the universe, we are not only exploring the outer space, but also the inner space of our own minds and imaginations. That's all for today's episode. Thank you for watching Curiosity. If you enjoyed this video, please like and subscribe for more content like this. And don't forget to share your thoughts and questions in the comments below. Until next time, stay curious